Before we look at how to solve the Eulerian cycle problem, there is one additional term that we need to be familiar with. An undirected graph is said to be connected if you can start from any vertex and reach any other vertex. This graph is connected because you can start from any vertex in the graph and follow some path to reach any other vertex. But if we were to delete this dotted edge, then the graph would become disconnected. It would split into two connected components. A connected component is a piece of the original graph within which you can start from any vertex and reach any other vertex. But you can't grow the connected component further by adding more vertices. It cannot be enlarged without losing the connectedness property. So for example, if I took this connected component and I pulled in this vertex here into the component, then there won't be a path from this vertex to these other 5 vertices since we have already deleted this edge. So then it would no longer remain a connected component. One may think that for a graph to have an Eulerian cycle, it must be connected. If it is not connected, it cannot have an Eulerian cycle. Sounds reasonable? But look at this graph. It is not connected. It has two connected components, but it does have an Eulerian cycle. A cycle that visits every edge of the graph exactly once. So it's possible for a graph to have an Eulerian cycle even if it's disconnected. But what we can say is that all the edges of the graph must belong to the same connected component. If they are not part of the same connected component, it would be impossible to visit them all. For our purposes, we will assume for now that our graph is connected. So all the edges are definitely part of the same connected component, right? If a graph is connected, there is only one connected component in it. Later on, we may come back and ask, how do we check that all the edges are part of the same connected component? For now, we will assume that they are. So here is the connected graph which we saw earlier with the Eulerian cycle marked on it. Now if you stare hard at the Eulerian cycle we have in this graph, you can make an interesting observation. The observation is the following. Remember that we started from this vertex, this was the start vertex, and this is where we ended, and all the other vertices were intermediate vertices along the Eulerian cycle. Now let's look at this vertex, for example. Every time we enter this vertex, we found a way to exit it along some unused edge, right? We entered it first along edge A, and then we left along edge B. And then we came back to it along edge D, and then we found a way to exit it using edge E. The same thing here. This is an intermediate vertex. Every time we entered it, we found a way to leave it. Right? We entered it along F after that, and then we left it along G. So this holds for every intermediate vertex if we have an Eulerian cycle. And even for the start vertex, for that matter, we left it at the beginning and then we came back to it at the end. So the observation we made is that every time we enter a vertex, we exit it along some unused edge. This is clearly true for all the intermediate vertices, and even for the start vertex, we exit it at the beginning and then we come back to it at the end. What this means is that if the graph has an Eulerian cycle, then the degree of every vertex in the graph must be even. Saying the same thing in different words, if the degree of any vertex is odd, the graph cannot have an Eulerian cycle. So let me write this down clearly. If there is an Eulerian cycle in the graph, then this implies that the degree of every vertex must be even. So this statement is equivalent to the statement which says that if the degree of every vertex of the graph is not even, that is, if the degree of any vertex is odd, then the graph cannot have an Eulerian cycle. So in logic, for example, if statement A implies statement B, that's the same as saying that if statement B is false, then the statement A must be false. And that's what we are doing here. We are saying if there is an Eulerian cycle in the graph, then the edges of the graph can be paired up so that every time we are entering an edge, we have an unused edge to exit along. So the degree of every vertex is even, right? The edges that are adjacent to any vertex can be paired up in that fashion. And so if we have even a single vertex in the graph whose degree is odd, then we won't be able to follow this process of always finding an edge to exit from whenever we come to that vertex. If there is an odd number of edges incident on that vertex, then we are going to get trapped. We're going to get trapped at that vertex at some point. So let's go back to the graph of the 7 bridges of Königsberg. If you notice here, every vertex in this graph has an odd degree. This vertex has a degree of 3, this vertex has a degree of 3, this vertex has a degree of 3, and this vertex has a degree of 5. So what does that mean? That means there is no Eulerian cycle in this graph. It is impossible to start from any vertex and to cross all the 7 bridges and come back to that vertex at the end. That's not possible. If we even attempt to do this, we're going to find that we'll get trapped somewhere. So I'm just making a random attempt here. Okay, I come back to this vertex, I leave it. Now if I go in that direction, I'm going to get trapped at this vertex. So I'm going to come back here to this vertex and then I leave it, and then I get trapped at this vertex, right? So there are two problems with this. Firstly, I left out this edge, and the second problem is I couldn't return back to the starting point. I got trapped at some vertex different from the start vertex. So this graph doesn't have an Eulerian cycle. We have mathematically shown it. Okay, we can try as many attempts as you want. You can try maybe a different path in this graph, but you're always going to get trapped. You'll never be able to trace an Eulerian cycle in this graph. How about these 3 diagrams we had? Let's start from the simplest of them. Remember that we can model this diagram as a graph where the corners are the vertices and the line segments, the straight line segments, are the edges. So if you notice, this vertex has a degree of 3. In fact, the 4 corners have a degree of 3, and this vertex in the middle has a degree of 4. So again, we have 4 vertices that have an odd degree, and from the argument we saw a few minutes back, that means there cannot exist an Eulerian cycle in this graph. So even if I make an attempt, let's say I start from here, I try to go in all various directions, trying to cover as many edges as I can, I got trapped here. Okay, I missed this edge, and I got trapped somewhere else. And you can try various options. You will always get trapped and you'll always miss out some edges. How about this diagram here? Let's say we represent this diagram also as a graph, and this time we have a degree of 4 for these vertices, we have a degree of 2 here, we have a degree of 4 here. So far it's looking good, but then we have these 2 vertices with an odd degree, and by the same argument we cannot have an Eulerian cycle in this graph. So even if we tried, let's say I start from here, I try to construct an Eulerian cycle. Okay, I did come back to the starting point, but I left one edge. So that was the problem. This was not an Eulerian cycle. So these two graphs won't have Eulerian cycles. How about this one? This graph, interestingly, has an even degree for every vertex. So this vertex has a degree of 4, this has a degree of 4, this has a degree of 4, 4, 4 and 2. So the degree of every vertex in this graph is even. Does that mean that there is an Eulerian cycle in it?